So, thanks for invitation. I'm Zeyu from Peking University, Beijing, China. My talk is about our paper, TreeGen, a tree-based transformer architecture for code generation. I will first introduce the introduction. It may often happen that when we want to implement a function like open a file F1, but we don't know how to implement it in a program language that we are not familiar with. Hopefully, a code generation system can automatically generate the target code like assign open F1 R to F in Python. Given a natural language description like open a file, the code generation system generates executable target source code. Such code generation is beneficial in various scenarios, including game development, learning, and so on. How to generate the code is important but challenging task in artificial intelligence. Given a natural language description like open a file, the code generation system will generate to solve this task, instead of directly using existing translators, sort approaches generate code by predicting a sequence of grammar rules. For a given code like assign to nouns, it can be represented as an abstract syntax string, namely AST. The AST of the code assigned to nouns is shown in the right, which can be gotten by parsing the given code in a set of predefined grammars. In this manner, the code is the AST and the AST is the code. They are the same. Existing approaches mostly directly generate ASTs by generating the rule sequence of it, and then transfer it into code. Such generated code is guaranteed to be syntactically correct. To generate such AST, we model code generation as a series of classification problems of grammar rules. AST-based code generation could be thought of as expanding non-terminal nodes by a grammar rule. For example, the node assign can be expanded by a grammar rule. Assign to target value with rule ID 10. And gets two child nodes, targets, and value. We repeat this processing until all leaf nodes are terminal symbols. In particular, for the next non-terminal node to be expanded, we always select the leftmost one. Formally, the probability of the target's AST can be factorized as probabilities of predicting rules. The predicting of grammar rules, which is also the predicting of the target code, faces two main challenges. The first challenge is the non-dependency problem, where a code element, for example, a variable reference in line 100 may depend on its definition, which may appear quite nice before, like the code in line 10. The second challenge is the representation of code structures. The code structure is represented as ASTs, and the structural information of ASTs is important. Like the node assign is the parent of the node value. However, a finite neural architecture such as an NN cannot capture structural information well. To address those problems, we propose a neural architecture TreeGen for code generation. We address the first challenge by adapting the recently proposed transformer, which can capture non-dependencies. However, the original transformer architecture cannot utilize the tree structures, and it is not designed for programs. Thus, we still have the second problem. A standard way of using structural information is to combine the vectors of a node and its structure neighbors, with its structure labels as the output of a structure convolutional sublayer. For example, combine the value of node targets with the node assigned. However, a standard this is a standard transformer architecture. The encoder is on the left, which contains the positional embedding, the self-attention sublayer, and the convolutional sublayer, and the decoder is on the right. If we directly add the structural convolution sublayer to the decoder, we will get such transformer architecture. In this architecture, the dense sublayer in the decoder is replaced by a structural convolution sublayer. However, there's still a question: to which transformer blocks should we add the structural convolution sublayers? It seems to be natural to add sublayers to all transformer blocks. However, we find as the vector repetition of the nodes is processed by more blocks in decoder, they gradually mix in more information from other nodes and lose their original information. For example, a given tree repetition and each node is represented as a real-valued vector. We first combine each node with its two ancestors via a structural convolution sublayer. The new vector representation of each node is extracted. Such a new vector contains the information of the original node and makes the information of the ancestors. And we get a new tree representation. We repeat the tree structural convolution and extract a new vector representation of each node again. The vector contains the mixed information of each node and its ancestors and the mixed information of the ancestors. And we get a new tree repetition again. For this repetition, we find the vector of node 3 mixes in more information from other nodes and lost their original information, such as node 2. For the task of code generation, our core conjecture is that when convolving a node and its structure neighbors, the vector repetition should mainly contain the information from the original node. Thus, we add the structural convolutional sublayer only to the first several transformer decoders blocks, but not all. Then I will introduce our approach. The TreeGen architecture consists of 3 parts. The first part is an NL reader, which encodes the input natural language description. And the second part is an AST reader, which encodes the generated partial AST with the structural convolution sublayers. The last part is a decoder which combines the query, namely the position information and the previous 2 readers to predict the next grammar rule. This is the overview of our approach, which takes natural language description as input and outputs the target AST sequence, rule sequence. After generation, the AST is further transferred to the code via a parser. And the details can be found in our paper, and I will not introduce the details here. In the last part, I will introduce the evaluation of our paper. We evaluated our approach on 2 benchmarks. The first is a Python code generation benchmark, Hearthstone. The Hearthstone dataset is an implementation of a card game Hearthstone. The example is shown on the left. The input is a semi-structured description, including the attributes like name, attack cost, and the description of a card. The output is an implementation of this card in Python. The second is two semantic parsing benchmarks, ATS and Zeyu. An example is shown on the right. The input is an natural language description, list airport in city, and the output is a program in lambda calculus. The experiment of Hearthstone is mainly the experiment of our approach. The benchmark contains Python code that implements 665 different cards of Hearthstone. The statistics is shown in the table. We use three metrics in the experiment. The first is string accuracy, which is the percentage of programs that has exactly the same token sequence as the ground truth. The second is blue, which measures the similarity between the generated code and the reference code at the token level. The last is accuracy plus, which is evaluated manually and allows the variable renaming on the top of string accuracy. Existing approaches pre-process the datasets in two ways. The first treats the input semi-structure description as the plain text. And the second treats the description as the semi-structure one, where the information of card attributes can be utilized. The experiment shows that our watch achieves 6 percentage points accuracy improvement with plain preprocessing and 4.5 percentage points accuracy improvement with structural preprocessing. We conducted an additional experiment to show that the structural convolution sublayer should only be applied to the first several decoder blocks, but not all. We also conducted an ablation test to show the importance of each component in TreeGen. We further evaluated the time efficiency. The experiment results shows that our approach takes least time among SOTA approaches. The second experiment is semantic parsing. The statistics are shown in the table. As shown, two datasets have fewer tokens in both the input description and the code, but more training data than Hearthstone dataset. We follow the evaluation of the previous approaches and use the accuracy as the metric, where the tree exact match was considered to avoid species errors. The results are shown in the table. As shown, the accuracy of our approach is slightly worse than the traditional approaches, which are based on the CCG parser and use a lot of templates. However, we achieved the best results among neural network-based approaches on both two datasets. To sum up, we propose TreeGen for code generation. TreeGen uses attention mechanism of transformers to elevate the non-dependency problem, and introduce an AST reader to combine the grammar rules and the AST structures. The experimental results shows that our approach significantly outperforms existing approaches. We also apply this framework to other areas, including code search. As a result, we published a research paper on AST conference called OCA and Overlapping Aware Code Retriever. Thanks for your listening.